So the first speaker is Rob Phillips. Rob Phillips is a professor at Caltech. Rob Phillips originally was a material scientist studying crystals, and 25 years ago he started to embark into the journey of studying living systems. And as a theorist, he's been using over the years the power of continuous descriptions, mathematical descriptions of the living to study different aspects of gene function, cell functions, organisms function. And so he's studying many, many different topics. And it's a real pleasure, Rob, to come in person to Paris, to come with us and to introduce us to a language whose characters are triangles. Sounds very Greek to me, and I can't wait to hear your talk. Thank you, Rob.
All right. Good morning, everybody. So it's great to be here. It's very bizarre to be in this room again and to see all of you with masks. This is a subject that I'm incredibly passionate about, as Thomas just said, and the talk today is one I usually give with my book co-author. We've actually written 2 books together, one of which is on active matter. It'll come out in a year or so, and we give it as a joint colloquium, and it's a pity that we're not doing this together. So just to start, I want to say that I think that the title of this symposium is probably one of the best that I've ever heard, and it brings together 3 words that really have been the basis of my intellectual life: mathematics, beauty, and the living. And I'll leave it up to you to decide if our birthday boy is beautiful or not. So for me, science really, beauty is subjective, I think. People argue about that, but I think beauty is subjective. And for me, the beauty of science actually is the fact that we engage with the mystery of the natural world. And I have such romantic notions. They really drive what I work on. And so already 2,000 years ago, Pliny the Elder commented on what he referred to as the troops. He used the word troops of starlings over Rome, which are well known to all of us. Lately, some of you may have noticed that there's this series of videos that appeared of drone videos of sheep. And you sit and look at that, and you can't be anything but fascinated by the patterns. And so the question is, what's the right language to describe a phenomenon like that? And I think, if I gave you the assignment of starting with a bunch of sheep that are robots and asked you to program them so that they would engage in that kind of behavior, the language that we would use is clearly mathematical. Another one of the themes that I'm going to touch on in my talk that I think is extremely important is that mathematics allows us to see the unity of phenomena that otherwise we would not even consider as being the same, if you'll let me use that word. So on the bottom, I show you some work from Stefan Grill. This is actin and myosin in a C. elegans embryo, and I'm going to make the claim today that those are flocks. Okay, so I'm going to talk about flocking theory, but in the context of the cytoskeleton. So the outline of the talk goes something like this. I'll spend a few slides just talking about the power and the beauty of mathematics. Given that, I'll talk about the main substance of what I want to say today, which is this incredible idea that we know the world's made of atoms, and yet it's sometimes much more powerful, even in the context of trying to understand mechanism, to replace those molecules with field variables. And I'll explain what I mean by that. And then once that's in hand, I'll turn to the question of the motion of certain parasites from the point of view of the theory of flocking. So the title is actually something that really has moved me. So imagine you're in the late 1500s, you have no clock, you're in a cathedral, and you notice the swinging of a chandelier, and you want to understand what are the regularities of that. Similarly, you know that bodies fall, and the thing that caught Galileo's mind, in the end, there's lots of mythology. But this guy was fascinated by the following observation. In successive instants of equal time, the distance traveled by a falling body went as the odd integers. Galileo knew that the sum of the first n odd integers is n squared, and he was blown away by this idea that somehow the falling of a body would be described by the mathematics of a quadratic function. This led him to make this remark: the universe cannot be read until we have learnt the language and become familiar with the characters in which it is written. It is written in mathematical language, and the letters are triangles, circles, and other geometrical figures. Now, you might think that that's poetic or hyperbole, but in fact, I don't think it's either of those things. I think it's bang on. And the first person to really nail that point was Newton. So in the Principia, he made this diagram. I think it's one of the greatest diagrams in the history of science. And again, that's not hyperbole. I mean that. And the reason is because what he did in this drawing is he unified the work of Galileo about projectile motion, which is this incredibly boring thing that we learn in some sort of high school physics class, and planetary motion. So he says, look, if I shoot a projectile off the mountain at V, it will form a parabolic orbit. But if I shoot it fast enough, it will keep falling over the horizon, and that orbit will be an ellipse. And the language for that is the language of second-order ordinary differential equations. But if you look in the Principia, the way he worked out Kepler's law of equal areas swept out in equal times was with the diagram on the right, and he showed that those triangles, the blue and the green one, and then there's another triangle that is beneath the blue one, that those three triangles are equal to one another using elementary geometry. And then he used what Steve Strogatz calls the infinity principle to imagine the triangle edge gets smaller and smaller and smaller so that this thing becomes a continuous orbit. So, you know, this notion of unifying things, of seeing sameness where otherwise you might not. When I first started out and learned about masses and springs, I thought, what are these physicists so obsessed with all these artificial systems for? It never would have crossed my mind that that would be the same system as a circuit made of a resistor, an inductor, and a capacitor. But in fact, they are literally the same. So this emboldened Wigner in the early 1960s to write this article called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. It's a really wonderful, super interesting article. And he marvels at the gift that we've been given, the gift that we can use mathematics to penetrate the mystery of the world around us. I don't think it's controversial at all to say that that point of view, the mathematical point of view, is dominant in physics. For me, I put a question mark under whether it's unreasonably effective in biology, because in many people's minds, that debate is still open. Although in my mind, that debate is over. It's a matter of dogmatism on the part of biologists. I'm sorry to think that biology is not describable by mathematics. Here I show you a beautiful example, which is the allele frequencies in a population of flies that have orange eyes. They're heterozygotes, very small population. You take them and you breed them, and over time, all of them will have either red eyes or white eyes. That's just drift. The mathematics is described by the binomial distribution. And maybe 10 years ago, I had the opportunity to speak. I was the last speaker at a great meeting at the Pasteur on the 50th anniversary of the allostery concept, the papers of Monod, Wyman, Changeux, and Jacob. And what I would say is that that model, the MWC model, shows us the power of mathematics in biology. So I just thought, you know, to try to make this point, I wanted to read you this little vignette from Wigner's article, because this is the point. It somehow shows you how crazy the mathematical description of the world is. So Wigner says, there's a story about two friends who were classmates in high school, talking about their jobs. One of them became a statistician and was working on population trends. He showed a reprint to his former classmate. The reprint started as usual with the Gaussian distribution. The statistician explained to his former classmate the meaning of the symbols for the actual population, for the average population, and so on. His classmate was a bit incredulous and was not quite sure whether the statistician was pulling his head. How can you know that, was his query, and what is this symbol here? Oh, said the statistician, this is pi. What is that? The ratio of the circumference of the circle to its diameter. Sorry. Well, now, I thought I spoke loud, Thomas. Well, now you're pushing your joke too far, said the classmate. Surely the population has nothing to do with the circumference of the circle. Naturally, we are inclined to smile about the simplicity of the classmate's approach. Nevertheless, when I heard the story, I had to admit to an eerie feeling, because surely the reaction of the classmate betrayed only plain common sense. What the heck? Why does pi show up when we're talking about probabilities? It's true. The guy's like, this is a crazy thing. So anyway, that's my little background. So now I want to talk about the power of field theory, which is a mathematical description of all sorts of different examples. And I'm gonna first just remind you that I think all of us are familiar with the notion of field. So we know that the atmosphere is made of nitrogen and oxygen molecules. But I experienced one of these fields 2 nights ago when I flew across the Atlantic Ocean. There's a wind, and always the wind is something that matters very much to fuel consumption and length of travel. This beautiful video shows you the wind patterns on the surface of the Earth. They're quite beautiful. And so the point here is that one has done what is called a coarse graining operation. We start out with molecules, we replace it with this notion of density and velocity. We draw little arrows. We no longer talk about molecules, we talk about a velocity field. This was so important that no less than Albert Einstein said, and this again is not hyperbole, he said, a new concept appears in physics, the most important invention since Newton's time, the field. So let me try to walk you through that. So let's imagine that we were interested in chemotaxis. We wanted to watch a neutrophil moving up some sort of a chemical gradient. We know that if we have our pipette, it releases individual molecules, these things that I show in red, and this notion of a field says, forget that. I'm going to replace it. At every point in space, I'm going to define a concentration field, and that's a scalar. It's a number at every point that tells me the number of molecules per unit volume. Now, as with many powerful concepts, this works across a great number of different scales. As I show you in the column on the left under density, you can see that Stefan Grill can use the field concept to describe myosin in a C. elegans embryo. But at the bottom, we know that the incredibly interesting work from the Italian physicists, I forgot their names, but it's a couple doing beautiful work where they're looking at the starlings from the same point of view of field theory. Over on the lower right, that's probably my favorite of all the diagrams. Many of you probably know about whales, where they make these patterns of bubbles in order to hunt fish. So what is a field theory? What would I mean by that? The way I think of it is a field theory is an update rule. I have some field, like for example, the density of molecules in this air, and I want to find out what happens a moment later. And so let's imagine this little thought experiment where I have this box that I show you. It has a partition. All the chemokine molecules are on the left side at t equals 0, and I want to find out what happens after that. Well, what happens is every molecule flips a coin. It either moves to the left or to the right. That's what actually happens. The molecules are just jiggling around randomly. But we can describe that using this very interesting equation that I write at the bottom. What does this say? It says the concentration at position x now is the concentration at position x a moment ago, and then plus all the molecules that jumped from the right into the box at position x, all the molecules from the left that jumped into the box at x, minus all the molecules at x that jumped either to the right or left. So that's the update rule. That's all you need to describe diffusion, and you can use that to solve a myriad of different problems. And I just think it's very amusing that when one writes down the mathematics, if you look in any book on diffusion, what you will see, damn it, it's an upside-down triangle. Galileo was absolutely right. It's a language whose characters are triangles. That's the Laplacian. So we solve this theory, and what you find is the distribution that I show you there on the right. The blue is the initial condition. All the molecules are on the left. There's none on the right. With the passage of time, you see the red curve, the yellow curve, the purple curve, and in the long time limit, the system is homogeneous, and the concentration has been halved. Now, I think this is really beautiful. I have to say, one of the greatest scientists in the history of science is Fourier, and you're a bunch of French people mainly. I cannot encourage you enough to read the first 40 pages of this book. I think you should read all of it, but it is mind-blowing. What Fourier wanted to do, he wanted to, in a certain sense, accomplish the same thing for phenomena like heat that Newton had done for mechanics. And he says that boldly. Just read it. He says himself, I want to do for heat what Newton did for mechanics. Here, just for amusement, I show you on a very late page in the book where he invented what we now would call the green function for diffusion. And he did it by Fourier transforms, if you can imagine. But one thing he couldn't do is the experiment that I show you in the upper right. So maybe 15 years ago, we were at the Marine Biological Laboratory in Woods Hole. This is with Jennifer Lippincott-Schwartz, Hyunjin Lee, and Jin Gillette. And we decided to photobleach on a keratocyte one of the great equations of diffusion, which is x squared equals 2dt. And on the right-hand side, what I'm showing you is the solution to that photobleaching problem using the method of finite elements, which I'm going to talk about in a little bit. It was done by my co-author, Christina. And what we calculated here is the time evolution of the concentration inside of the keratocyte after you do this photobleaching as your initial condition. And what I would say is, we're solving an equation described by that upside-down triangle. So another aspect that I think is very amusing is let's imagine that I have a fluorescent molecule like GFP that I show you on the left-hand side. And then what I'm going to do is I'm going to ask each of you, I know, Thomas, were you born on an even day or an odd day?
Odd.
Odd. Jean-François, even or odd? Even. Hervé, even or odd? Odd. Okay. What I'm doing is I'm just flipping a coin, okay? I'm flipping a coin, and I'm moving left or right, depending on whether the answer is even or odd. That is diffusion. And you can see on the right-hand side, the upper right, that those are the trajectories. If I just kept doing this experiment, I would have been moving left and right. And the thing that's amusing about that is that the probability of being at different positions is described by the fractions that I show you on the left. And the beauty of this is that those fractions, the numerators, are given by nothing more than Pascal's triangle. Once again, a language whose characters are triangles. So now what I want to do is I want to get serious about a particular case study, and that's the case study of flocking. Okay, so I've told you a little bit about field theory. Now what I want to do is I want to try and attack that problem from the point of view of notions of field theory. So if I were to call my mom and I wanted to describe to her the nature of the murmuration of starlings, what would I tell her? If she wanted to draw a picture, what would she need to know? She'd need to know the positions of the birds and how dense they are, and then how fast they're moving along. So we need to write equations that tell us how the velocity of the birds and their density changes over time. So that's what I mean by this notion of the field theory. Let me give you an example of how one would construct a theory of the update. I told you that the equations that we write down are update rules. The fancy name is partial differential equations, but really they're update rules. So the bird number 2 wants to decide in the next instant of time, what should it do to change its velocity? What it's going to do is democracy. It's going to consult its neighbor, number 1, and it's going to say, how fast are you going? And it will take the difference between its speed and the bird number 1, and that will be pointing to the left. Then it'll look at the bird to its right, which is bird 3, and it'll say, how fast are you going? It will take the difference, and then it will get the vector that I show you on the right. Then it will say, what I'm going to do is I'm going to try to be democratic. I will average over all those differences, and I'll use that to decide on how much I change my speed. And so that gives you, as I show you in the bottom, this upside down triangle squared. So I like that because this so-called Laplacian is basically a rule for smoothing out or for democratically partitioning the velocity. Again, it's what you do on the highway, you know, if you're not riding a scooter and sort of going between the lanes. You kind of take stock of your neighbors and you figure out how fast to go. And in fact, I've tried to do experiments on our psychological viscosity. You know, how much velocity difference are you willing to tolerate in the highway? So there's this theory that's called the Toner 2 theory. I'm not going to go into the details of it because they don't matter. The point that I'm trying to make is that there's an update rule where on the right-hand side, it's all the things that the bird does to try to decide what speed should it have. There's a preferred speed. There's a punishment for having a gradient in density. There's the smoothing term that I told you about, and then an advection. Okay, so now I'm going to basically take these ideas and I'm going to unleash them in the context of a fun biological example. So what I've told you so far is about this idea of field theory, but I've also argued that it works across many different scales. And to me, that should be one of the themes of the day, is that mathematics allows us to actually see, as I already said, that different phenomena that seem apparently completely disparate are in fact the same thing. So what I want to do is I want to now try to demonstrate to you that the motion of this humble parasite, Toxoplasma gondii, is actually related to flocking. So we're going to take a huge leap across the eukaryotic tree of life. So we started in the lower right with birds, and now we're going all the way across to those purple guys, the Apicomplexa, which includes Plasmodium, which is the causative agent of malaria, and then Toxoplasma. I actually heard the other day, I don't know how many, if somebody at the break wants to tell me, so I think that in the population at large, more than 1/3 of people have Toxoplasma cells within them, and somehow in France it might be higher because of eating raw meat. I don't know that, and I'd like to hear whether any of you actually know about that. So at any rate, these little 5-micron cells, they have a different form of motility than we're usually used to. Usually we're used to eukaryotes either swimming, or alternatively they undergo shape changes and they pull on surfaces. These guys undergo a rigid body motion, and they have a great diversity of different modes of motion. So in the top, you see helical gliding. Sometimes they do circular gliding. Sometimes they do this twirling. And sometimes they do this back and forth motion. And the question that Christina had was, how does surface actomyosin drive all these distinct movements? And so what I'm going to do is try and walk you through the idea that a flocking theory of actin actually can help us understand how this works. So the cartoon is meant to show you that there's a very thin, let's say 25 nanometer layer between the plasma membrane and the inner membrane complex, which is shown as that little double thing in yellow. And for those of you that have actually seen these movies of what are called gliding assays, here's the picture. You have a surface, you decorate the surface with myosin molecules, and then you fluorescently label actin filaments and you lay them down. And what happens is they spontaneously glide around on the surface because the motors are doing this and causing them to move. And so that's the concept, is that the motors are fixed and the actin filaments are moving around really fast. And that's something that many people have looked at and Christina looked at in detail using single molecule microscopy. So here's the fundamental question that you might ask. And actually, Thomas has a beautiful slide that maybe some of you have seen him give, where he shows a Norwegian cathedral and then also a termite mound. The Norwegian cathedral is built on templates. You have a blueprint and there's a certain way of constructing it. But a termite mound is actually self-organized. And so here the question is, people had thought, the hypothesis in the field, or at least a lot of people had thought, that the gray microtubules, you'll see these things that are coming down, those microtubules patterned the actin in some way. But an alternative is the idea that the actin actually self-organizes. And so the sense in which we're going to use the flocking theory is that we're going to assign a density field. There's a certain density of actin. We're going to assign a velocity field. And then what we want to do is we want to try to solve for the dynamics of these filaments. So once again, there's an equation that describes conservation of mass. It's accounting. A lot of mathematics of field theory is about accounting. You take a little box and you ask the question, how did the stuff inside of the box change? Well, one of the ways things change is because stuff came in one side and went out the other. So that's what this equation accounts for. Then for the velocity, we have all these different terms that I already talked to you about. So let me just quickly comment on them. So there's the intrinsic speed of the molecular motors. So that sets a preferred speed. The filaments tend to align with each other. That is to say, if I have two filaments that are nearby, they will tend to orient because of either excluded volume effects or because of cross-linking proteins. I already mentioned this pressure term. And then the last term that's new here, that's usually not present in a flocking theory, is that the filaments want to bend away from the direction of maximum curvature towards the direction of minimum curvature. So we have the same equations that I told you before, but we do not want to solve the problem of a spherical cow. So I have to confess, with a physics background, I've always loved the notion of a spherical cow, and I felt we should not apologize for it. I think it's a very useful thing. But in this case, the shape of the cell actually confers the interesting and rich dynamics. So we wanted to solve the problem on this curved surface with arbitrary geometry. We know the structure from soft X-ray tomography. And the way we're going to solve this is, once again, appealing to triangles using a method called the method of finite elements. But probably many of you are very aware that all sorts of different occupations, such as Hollywood, when they make the Beauty and the Beast or whatever, animations, it's through triangulations, again, in the language of Galileo. So what do I mean by triangulation? It's very cool. We started out with molecules. We then made a field theory of density and velocity, and now we're going to go do a different discretization. We're not going to do a molecular discretization, but we're going to represent the cell by a series of nodes, these vertices that I show you. And then we're going to interpolate using methods that were developed, for example, by Lagrange, actually. And we're going to interpolate the fields in between. So let me give you an example of how this looks. So I'm going to skip this. So the way we do this is we're solving the equations for flocking on a surface. And what I want to show you is this is a time evolution. And what you see is the colors tell you the density of the filaments, and the arrows tell you the direction that the filaments are moving. And what I hope you can appreciate and see rather clearly is that the solution here leads to a periodic moving density across the surface. And this is something that Christina was actually able to observe. She stabilizes the actin filaments. We call this the narwhal because it looks like one of those whales that has the long horn. You can see the actin filaments, the bundle of actin filaments circulating around the cell. However, we know that unlike a flock of wildebeest, as it's moving around, the number of wildebeest does not change on the time scales of walking across the Serengeti. But we know that actin can be nucleated and can polymerize, which takes place at the North Pole, the so-called conoid of these cells. We also know that actin can be depolymerized, which I represent by scissors at the bottom. So if we put in that actin dynamics, what you'll see is actually this thing develops a stable, steady state. So instead of being periodic, if we tune the parameters in the right way, then we actually get a stable, steady state. And the claim I'm going to make, this is a hypothesis, is that basically these two key facts. One is, are we in the periodic regime or are we in the stable fixed point regime? And then which part of the cell is touching the surface? The answer to those two questions is what gives rise to these 4 different modes of motion. Again, I can maybe talk to people about it at the end. So I'm basically done. So what I hoped to get across today was, well, first of all, I'm incredibly grateful to be here. I'm glad I'm the first speaker because now I can focus on listening to these really interesting, diverse talks. And I think it's good because mathematics is a tool for us to come together in the diversity of biology. I wanted to sort of follow up on this Galileo statement because I do think it's rather amazing. We all learn, the first thing we learn in geometry is the Pythagorean theorem, shown there in the upper left. And yet, Pierre Sans, Jean-François Joanny, they've written papers on membranes, and in the end, they wrote an equation. And there's an integral with a square root of 1 plus a derivative squared. That is the Pythagorean theorem, and it applies to things like the membrane pooling and all sorts of stuff like that. The middle column shows you the motion of kinesin on a microtubule. The kinesin is shown in red. And I just think it's very amusing that the Pascal triangle tells us how to understand how that plays out. And then the finite element method is based on triangles as well. I think I'll skip this. Let me end, maybe we can take 10 seconds of silence and just enjoy watching this. So we'll start this video. You probably can't hear it very well. Yeah, I just want to make sure you saw that part. So why am I showing you this? There are mysteries all around us. And although it's easy for us to look at this, in classical elasticity, we know very well how to take a material and push on it and figure out what the elastic deformations will be. What I would say, we know very well. This is something that was worked out by Hertz in the late 1800s. But as far as a sea lion impinging upon a school of fish, that we do not know how to solve that problem. There is no sea lion green function, so to speak. And I guess I think it's a wonderful thing for us to think about these kinds of mysteries. And this one in particular, I think, is something that I'm going to enjoy working on in the years to come. So in the end, I want to make a special call out to my book co-author shown there on the left. And really, this is the work of Christina Hieschen, the person with the square around her, and she works in the lab of Alex Dunn at Stanford. And those are some of our collaborators and friends. And again, thank you very much for having me here.